So let's have a look at this patterns question from the 2015 Junior Cert Higher Level Sample Paper 1. It's question 8, and we've been given the first 3 stages of a pattern and asked to draw the next 2. Most people don't find too much difficulty in a question like this where you have to draw subsequent stages in a pattern, but because of the large number of boxes in this question, it can get a little difficult, especially when it gets to stage 5. What I would do first is I would count how many wide and high the shape is. So stage 1 is 1 box wide and 1 box high. Then stage 2 is 3 wide by 3 high. Stage 3 is 5 wide by 5 high. And so we can see that there's a pattern here where we're adding an additional box above and below and to the left and to the right. And then we're going to fill in the arms around the shape to make it consistent with the rest of the shapes. In drawing stage 4 then, we're going to draw 7 boxes high and wide. And then we're going to fill in the arms. So we need an additional 3 boxes in between each of the arms. Stage 5 is going to be 9 wide by 9 high, and again, to make it look consistent with the rest of the patterns, we need to fill in 6 boxes inside each of the arms. So the B part of the question tells us that the perimeter of stage 1 is 4, the perimeter of stage 2 is 12, and then they ask us to find a formula for the perimeter of stage n of the pattern, where n is a natural number. So when we're talking about the perimeter is the distance around the outside of each of these shapes. And we've been given the first 2, so stage 1 is 4 and stage 2 is 12. The important thing here is to establish what kind of a pattern is this going to be so that we can find a general formula. Is it going to be linear? Is it going to be quadratic? So if we make a table and put in the information we found already, so 4 and 12, and for stage 3 we are going to have to count the outside, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the perimeter of stage 3 is 20. And at this stage we can see that the gaps between each of these is common. So the gap is 8. We're going up an additional 8 in each stage. So this is a linear pattern. So we can confirm this by counting all the sides on the outside of stage 4, and we'll get 28. And then stage 5, if we add another 8, we'll get 36. So we have a linear pattern, and in a linear pattern what we do is we take the difference, which this time is 8, and we multiply it by n, and then we decide what are we going to have to add or subtract to that to get the number we want. So if I multiply 8 by 1, I have the number 8, but I'm looking for 4, so I'll have to subtract a 4. For pattern 2, 8 by 2 is 16, but I need 12. So I subtract 4. 8 by 3, well, 8 by 3 is going to be 24. I need to subtract 4, and that will give me the 20. So the formula is going to be found by multiplying the difference by n and subtracting 4. And again, if we just try that with the first few numbers, 8 by 1 minus 4 is 4. 8 by 2 minus 4 is 12. 8 by 3 minus 4 is 16. And so clearly our formula for the general term of the perimeter of these shapes is perimeter is equal to 8 by n minus 4. So P is equal to 8n minus 4. Part C, the question asks us to find a general formula for the area of stage n of the pattern, where n is a natural number. The previous part asks us to find a formula for the perimeter of these stages, and now we're being asked for the area, so the amount of space inside each of the stages. One box in this question is 1 square unit, so to find the area of each stage all we have to do is count the number of boxes. So in stage 1 we have 1 box, stage 2 we have 5, stage 3 we have 13, and stage 4 we have 25. Before we can find a general formula for the area of the stage n, what we have to do is establish what kind of a pattern this is. So again, the best way to do this is to write down the sequence 1, 5, 13, 25 and find the differences between the terms. So the difference between 1 and 5 is 4, 5 and 13 is 8, and 13 and 25 is 12. The first difference isn't the same, so it's not a linear sequence. And so what we need to do now is to find the differences between these differences. The difference between 4 and 8 is 4, and 8 and 12 is 4. A pattern where the second difference is the same is called a quadratic sequence. Like I said, had it been a linear sequence, the first difference would have been the same, and that was the pattern that we had in 8b for the perimeter. So there's a number of different ways that we can find the general formula for a quadratic sequence. The way we're going to look at first is by using the formula for a quadratic sequence, and then we can look at an alternate method which uses a more visual approach. So the first thing about using this formulaic approach to find the general formula for a quadratic sequence is that it is more time consuming. If you can look at the diagram and visually gather enough information to create a formula in n, it is more preferable, but this is a method that works all the time, and even if you are that sort of a student who can pick the formula quite easily from the sketch, it's a good idea to use this method then to check your answer, especially if you have time at the end of the exam. You're going to have to learn the formula, which is Tn, the general term, is equal to an squared plus bn plus c. And what we're going to try and find in this question is a, b and c. To start with, we let the second difference, which we've already found from the previous part, 4, equal 2a. So it's always 2a. We always let 2a equal the second difference. So 2a is equal to 4, and that means that a is equal to 2. So for the rest of this question, a can be 2. So we update our formula. So our formula was an squared plus bn plus c, and now we know a is 2. Our formula that we can use going forward is 2n squared plus bn plus c. So the question becomes, how do we go and find b and c? Well, if we look up here, we can see that the first term, t1, is equal to 1, which means that if I take this sequence and sub in 1, the whole formula should be equal to 1. So we'll do that. We're going to sub in n equal 1 into the formula, and we're going to let the whole formula equal to 1. When the input is 1, the stage term, the output is 1, the number of squares or the area of the pattern. So tidy this up, when we get 2 plus b plus c equals 1, we'll subtract 2 from both sides and we'll be left with b plus c equals minus 1. So we have an equation in terms of b and c. So we're going to need to find another equation in terms of b and c, and so similarly, term 2 is equal to 5, which means that if I sub in n equals 2 into my formula, the whole thing should be equal to 5. So I write down my formula again, and I'm going to put in 2 for n, the stage number, and when the input is 2 for the stage number, the output, the area, the number of squares is equal to 5. So we tidy this up. We have 8 plus 2b plus c is equal to 5. We subtract 8 from both sides, and we get 2b plus c is equal to minus 3. So we have two equations here in b and c, and so to find the values of b and c, we're going to do a simultaneous equation. So we write one above the other one, and we can see that the c's will cancel here quite easily if I can change the signs of the bottom line. So how do I change the signs of the bottom line? I'm going to multiply the whole bottom equation by minus 1, and I get minus b minus c plus 1. C minus c is 0, and so that's going to cancel, and I get 2b minus b is 1b, and minus 3 plus 1 is minus 2. So now we've found the b term, so b is equal to minus 2. If we sub this back into the original equation, b plus c equals minus 1, we get minus 2 plus c is equal to minus 1. We're going to add a 2 to both sides, and we get c is equal to 2 minus 1, and we get c is equal to 1. So now we've found the a, b, and c terms for the question. We're going to sub these back into our formula for the general term for the area. So our formula was 2n squared plus bn plus c. We found b and c, so we're going to sub them into our formula. And we've now created a general formula for the number of squares in each stage, or the area in each stage. We just want to test this formula to make sure that it works. So let's sub in 3 into this formula, n equals 3, and see do we get 13 squares, which we should. So if I take the formula and I'm going to sub in 3 everywhere I have an n, so it's 2 by 3 squared minus 2 by 3 plus 1. So 2 by 3 squared is 18, minus 6 plus 1 is 13. And so our formula does work, and if we're able to input into the formula the stage, well, the formula will tell us the area of that stage, or the number of squares in that stage. So let's have a look at a more intuitive and visual way to do this question, finding a formula for a quadratic sequence in terms of n by breaking down the shape that we have in each stage. The method we've outlined on the previous page is probably more preferable to learn in terms of it's something that always works for a quadratic sequence. We can learn the methodology and we can apply it to any quadratic sequence. Whereas if we use this more visual approach, every shape will be different and every question will be different, and the method we use will change depending on what we spot on that given question. So in this question, I decided to break the shapes up into colors green and purple. And what I'm going to do is I'm going to find a formula for the green shapes in terms of n, and then I'm going to go and I'm going to find a formula for the purple shapes in terms of n. and the purple and the green I'm going to add together to get an overall formula for the number of squares in each of these stages. So to take the green squares first of all, if we can spot what's happening here, it's a good idea to write the number of green squares. So in stage 1 we have 1 green square. So when n is equal to 1 we have 1 green square. In stage 2 we have 4 green squares. So when n is equal to 2 we have 4 green squares. When n is equal to 3 we have 9 green squares. And so we might be able to see what's happening to the n term to get the number of green squares in each subsequent stage. So we're actually squaring the pattern number. So what we can do is we can say that the formula for the green section will be n squared. If we go and have a look at the purple section then, the purple section is doing a similar thing, except in stage 1, when n equals 1, well, the number of purple squares is 0. When n equals 2, the number of purple squares is 1. When n equals 3, the number of purple squares is 4. And when n equals 4, the number of purple squares is 9. This is much harder to spot what's happening with this pattern. We can see that there is a pattern, 1, 4, 9, but it's a stage different than the green pattern. So what we're going to do is, if we say we subtract 1 from the nth term and then square it, we'll end up with the number of squares. So for example, when n is equal to 1, if we subtract 1 from that, we get 0. 0 squared is 0. When n is equal to 2, subtract 1 from 2, we get 1. 1 squared is 1. When n is equal to 3, subtract 1 from that, and we get 2. 2 squared is 4. And finally, when n is equal to 4, subtract 1 from that, we get 3. 3 squared is 9. So for the purple squares, we can see that what's happening for the general term is that we are subtracting 1 from n and squaring it to give us the number of squares in the purple section. Okay, the final thing is, if we want an overall formula for the number of squares in each stage, we need to add these two things together, because they're only giving us the number of green and number of purple squares respectively in each stage. The total number of squares in a stage is found by adding those two things together. So if we add n squared, so that's the number of green squares, to n minus 1 squared, the number of purple squares, we're going to tidy this up by multiplying it out. So n squared plus n minus 1 by n minus 1, which is n squared plus n squared minus n plus 1. And finally, if we tidy this up, n squared and n squared is 2n squared, minus n is minus 2n plus 1. And this is the same formula that we found on the previous slide. So some people might find this method preferable, but again, spotting that this can be split up into these two different patterns can be quite difficult to do, and so it is good to have a structured methodology that works every time, which we got on the previous slide. The D part asks us what kind of a sequence, linear, quadratic, exponential, or none of these do the areas follow, and it asks us to justify our answer. Now we've already established in the C part that this is a quadratic sequence, but it may have been a case that you took the visual method, and if you had taken that method, you may have not found the second difference between these terms and established that it was the same. So most sequences, when we're trying to find out if it's linear or quadratic initially, what we do is we take the differences between the terms, so 4, 8, and 12. If they're the same, then it's a linear sequence. The first difference is the same. If they're not the same, then we go and we try and find the second differences. So if the second differences are the same as they are in this case, it's a quadratic sequence and we can stop there. If the second differences hadn't been the same, we might investigate whether it was an exponential sequence. So an exponential sequence is one that's being multiplied by a common term each time. Just make sure that even though we have these workings here and we found the second difference, you do want to write down that since the second difference is the same, we can say it's a quadratic sequence. If you don't write a sentence afterwards, it is possible that you might lose some marks.